Good afternoon, everyone. Thanks for attending my talk. And I'm happy to have this opportunity to introduce our research work on the reconfigurable computing architecture. Although this is not directly related to RISC-V, but our work is for the general CPU FPGA architecture, and hopefully it will be interesting to you, and then can be applied to your RISC-V design. And it's happy to meet you all. In the later slides, I will be turning off the camera, just trying to save some recording space. So this is a brief introduction to our lab. So our lab is called Reconfigurable System Lab. It has like several PhD students and a few students from all over the world. And the Reconfigurable System Lab was established in 2013 when I first joined Hong Kong University of Science and Technology as assistant professor. So our research area has been focusing on the reconfigurable system and FPGA-based design. So our work actually has ranging from underlying architectures to the synthesis flow and to the upper level applications. And we're developing the corresponding EDA tools to help on the FPGA mapping flow. And we also work on a little bit on the high performance, low power system to minimize the power and improve the thermal and power management. And we also have works on the embedded system security and emerging technology. So in the past years, we have published over 100 papers in conferences and journals. We have the best paper nominations in cases, stack, and we also got best paper award in ICCAT 2017 and ISVRSI 2009. Our team has been collaborating with many industries such as Xilinx, Huawei, and Alibaba Electro. So this slide lists some examples of our major projects, including the accelerator design, reconfigurable architecture, and the synthesis flow. So for the architecture design, we mainly use the IPGA as hardware accelerators to accelerate the computation-intensive and data-intensive applications such as deep neural network, database query, and graph processing electro. And for the reconfigurable architecture and heterogeneous system, in the past, we have been developing the novel FPGA based on the emerging technologies. And in our recent work, so we work on the cache management for the emerging shared cache heterogeneous system, which are proposed by the Intel and IBM, such as systems like Hub and Power 8. And so in this talk, I will mainly introduce our cache management works on this shared cache CPU and FPGA heterogeneous system. And we also develop the simulators or the evaluation platform for people to develop their novel cache architectures for this heterogeneous system. So then for the synthesis flow, we try to optimize mapping performance and like the power efficiency from perspectives and at different level for the IPGA. So in our recent work, we mainly focusing on the high-level synthesis. So for this talk, I will also introducing several our automatic optimization framework for the high-level synthesis flow. Okay, so in this talk, I will first briefly introduce several automatic optimization works for the high-level synthesis design for FPGA, and follow that, I will focusing on our works on the CPU and FPGA heterogeneous system. I will first introduce our full system simulator, and for the simulating of the novel designs for the heterogeneous system with different types of cache hierarchy, and then I will introduce that our cache management scheme for the systems like the Hub system, and to improve the cache hit rate of FPGA and also corresponding the performance of the whole system. So this methodology is a general methodology, so it should be applied to different CPUs and accelerator system. So it should be also be useful for the CPUs such like RISC-V. Okay, so maybe some of you are not familiar with IPJ, so I would like to take some minutes to introduce the IPJ background. So what is IPJ? Then IPJ is a reconfigurable architectures composed of reconfigurable logics such as lookup table, flip-flop, DSP blocks, and memories on chip, and also the reconfigurable interconnect. That so IPJ can be configured to implement different functions at different time. So if compared to the other computing platforms such as the CPU, GPU, and the ASIC, so IPJ has an overall advantage that it has like high performance compared to CPU and lower power consumptions than CPU and GPU, and it has like more flexibility than ASIC because it's a hardware programmable. So it relatively has a short time to market. And due to this overall advantage, IPJ is actually getting increasingly usage in different fields. Traditionally, it is used in like image processing, wireless communication, electro. So recently, it also gets widely used as accelerators in the data center. So also IPJ is getting increasing attraction. However, there are still many difficulties to be overcome first before IPJ can be more widely used into different fields. One difficulty IPJ design is facing is its design flow. So traditional IPJ design flow starting from the RTL design use hardware description language. So the developer need to write their design using the HDL language and with the hardware architecture bear in mind. And then this RTL design can be synthesized automatically into the IPJ. However, to write an efficient RTL design, the developer need to have relatively solid hardware knowledge before it can really tune the design to be the best. And we can see that there's actually a big gap between the RTL design with optimization and without optimization. However, it would be hard for the people, especially the software designers who doesn't have solid hardware background, to tune the design parameters and to debug the mistakes in the RTL design. So this gives a very high barrier for the IPJ to be used by the software designer. In order to solve this challenge and lower the barrier for the software designer, high-level synthesis was developed and recently getting more and more popular. So high-level synthesis allows the designers to specify their design at a high level using language such as C, C++, OpenCL, Python, Electro, and then the high-level synthesis synthesis tools can automatically map this design to the RTL design and then further synthesize it into IPGA. So we can see that the programmability of IPGA is significantly improved, and the design flow is more friendly to the software designer. However, things are not so simple as the designer just need to write their C or C++ code. Actually, there are also very important design parameters to be optimized or to be set. Those parameters are called derivatives or pragmas. Those parameters specified like if the functions will be pipelined, the loops, how to parallelize it, how to unroll the loops, and arrays, how to partition the electro. So we can see that if we want to set the derivatives or parapragmas to be optimal value, actually it requires the designers to have some hardware design knowledges, and then they know that how to parallelize the design on the IPJ. So it is not easy for the software designer. So it will be helpful to develop an automatic searching and optimization framework to search for the optimal derivative settings. However, this is also not simple because we have a very huge search space considering the different variables of the derivatives. So we need an efficient method to automatically search and set the derivatives in a short time and with a high performance designs generated. So in order to address the mentioned challenges, I introduced our work for the performance automatic analysis and optimization framework. So this work, compared to the previous work, firstly consider more directed settings for the functions, loop, and array, and also it's the first time consider the real more complex code structures or C or C++ code. So the flow takes iterative improvement every round, and for the current round, it gives accurate estimations of the performance based on our analytical performance model, and then identifies the bottleneck. So after that, our optimization advisor will give the guidelines on how to optimize the derivatives to solve the current bottleneck. So with this performance modeling and the efficient optimization advisor, so every round and the performance will be significantly improved. So even the design space is very huge. Our framework can search this huge design space in a very fast speed. And the experimental results show that our analytical model achieves accurate cycle number estimation with only 1% to 5% the error rate. And the flow compared to the previous searching flows, it has speed up hundreds of times even for the much bigger design space. So we also applied this performance optimization framework on the CNN implementation on FPGA, because when people implement CNN on FPGA, there's so many different ways of implementations, and it's hard to see which way is the best one. So then we use this automatic searching framework to optimize the CNN implementation on FPGA. So first of all, we present the CNN design using an efficient data structure called loop tree, and then we use the coarse grain model first and then fine grain model to estimate the current round of CNN implementation performance, and then we utilize the performance advisors to guide the optimization of the derivatives or the optimization of the designs gradually. So then finally we can choose the optimal design, and experimental results show that our model are very close to the onboard running results, so showing the accuracy of our model estimation, and also we can successfully search and achieve the best design of the CNN optimization for different CNN networks, showing the efficiencies of our optimization framework. Due to time limit, I will skip our other works for FPGA-based synthesis flow, and next we will discuss on the heterogeneous computing, where FPGA is used as a coprocessor to work together with the CPU. So CPU and FPGA heterogeneous system has been widely used in different applications. Its advantage is clear that it can provide more data parallelism and deal with irregular data processing and improved energy efficiency and performance. However, such system is also facing some problems. For example, traditional CPU and FPGA system is connected through PCIe, so they have separate memory space. CPU and FPGA need to be programmed separately. Then the task to be implemented on FPGA will be uploaded from CPU memory into the FPGA memory, which will cause a long delay. So in order to improve the efficiency of this CPU and FPGA system, so emerging types of CPU FPGA heterogeneous system has been proposed by Intel and IBM Electro. So you can see that such emerging architectures in Think, Intel Hub system, or the IBM Power 8 system. So in Think, ARM core connected with is connected with FPGA fabric through shared cache ACP port, and Intel Hub system CPU and the FPGA also share the L2 level cache, and the data can be directly transferred from the L2 cache, and the programming model is also unified. So for the Power 8 system, CPU and FPGA is connected through the CAPI port, so they also can share and transfer the data through the cache. So this greatly shortens the communication delay for the data transferring between CPU and FPGA. So we can see like 3 different memory hierarchies between CPU and FPGA. So traditionally, FPGA and CPU is connected through DMA. Then for the new type of systems, FPGA and CPU share and transfer data through the last level cache. So for FPGA itself, it can have its own FPGA cache or skip the L1 cache. So the question will be interesting that which memory is the best for the CPU and FPGA coupling for what kind of a situation, and when we're trying to explore different benchmarks, so what the trade-off would be. First, in order to enable the architecture exploration for the heterogeneous system, we developed full system simulators for CPU and accelerator system. The accelerator can be FPGA or ASIC, and the full system simulator is based on Gem5 and Validator. Validator is used for the simulations of the accelerator, and Gem5, we all know that it's a very powerful CPU simulator. It can support different types of cores and different types of on-chip network, etc. And then we developed the integration between CPU and FPGA, so it can simulate different types of memory in the cache hierarchy between CPU and FPGA. And we also parallelize this simulator that it can run faster. And we verified our simulator with Think SoC, and we found that the error is less than 5%. So this full system simulator is quite fast and accurate. So we will use it to evaluate different benchmarks on different types of cache hierarchies and show the trade-off later. With the different benchmarks, we explore these 3 different memory hierarchies. And with this experimental result, we see that at average, the architecture with shared cache between CPU and FPGA has much better performance compared with this DMA memory hierarchy. So we can see that 70% for performance improvement can be achieved. This is due to the significant reduction of the communication overhead between CPU and FPGA. So we can see that for at least the benchmarks we explored, which is a typical embedded system benchmarks, and then the shared cache between CPU and FPGA could be helpful. But if we look further in the cases for L1 cache for FPGA, if it is beneficial or not is actually not so clear because it varies with different benchmarks. So for some benchmarks, this FPGA has L1 cache achieves better performance, and for other cases, skipping L1 cache could be better. So it varies with different benchmarks. It also means that the acceleration functions on FPGA, its characteristics actually affects the performances of the benefits of the L1 cache. So the questions interesting to be answered is basically in which cases we will need the L1 cache for FPGA, and in which cases we should skip the L1 cache. So we will observe that for some cases, the FPGA cache could be helpful, but FPGA cache size is limited and data will compete for the FPGA cache. And we also see that there could be large overhead for the FPGA cache miss. So in order to best utilize the FPGA cache, we should reduce the competition, and it would be better to have a strategy to decide that what data to store on FPGA cache and what data can be bypassed. Then in order to solve this problem, we also observe that in most cases, we will know the typical input for the FPGA accelerator. Hence, it enables the compile time analysis. So we propose a hybrid cache bypassing scheme, which is composed of compile time analysis and runtime control. And at compile time analysis, we will compute the data reuse distance and to see if this data has a good locality, and also provide the hints for the runtime bypassing. Then during runtime control, so we will look at the compile time analysis and decide that for the good data locality, so we can store this data on FPGA cache. And for the data with bad locality, we will bypass it to reduce the pollutions and competition for the FPGA cache, and correspondingly to reduce the cache miss of this FPGA cache. And from this strategy, we can see that it can significantly improve the FPGA performance and correspondingly the whole system performance. So this slide illustrates our static classification and dynamic bypassing scheme. So for the compile time analysis, first of all, we will collect the memory traces of the accelerator and then compute the real distance of each exercise. According to the analysis, we will classify the data into three types: H type, L type, and M type. For H type, it means it has high locality and it should be stored into FPGA cache. And for L type, it has low locality and we should perform bypassing of the cache. And for the M type, it has the medium locality level, so its caching or bypassing is not decided at the compile time. Actually, we will see the runtime situation and to decide what to do at runtime. So then we will use this figure animation to illustrate how the runtime control is performed. So first, the accelerator will send the access to FPGA cache to retrieve some data. If it results in a hit, so the data will directly return to the accelerator. Otherwise, if there's a cache miss, then the request will go to the last level cache to retrieve the missed cache line. And when the cache line is returned, then we will look at the bypassing controller's decision and to see that it will do caching or bypassing. So the controller will check the classification table and to see this data type. If this data is a H type data, then we will definitely cache the data into FPGA cache. And if it is a L type data, so then we will perform the cache bypassing and then we directly send the data back to the accelerator without storing the data into FPGA cache. So by this way, it will be reducing the pollutions for the FPGA cache. And if this is a M type data, actually we will use a learning mechanism to decide we will do the caching or bypassing. So we assume that in the recent time or the short period time, and then the M type data will have the similar characteristics or similar locality. So we will see that if recent M type data has give a good hit rate for the FPGA cache, then that means this M type data probably will have similar locality and it can be stored into the FPGA cache. Otherwise, if recent M type data has a bad locality and results in a lot of cache miss, then we will also bypassing this M type data. So according to this runtime decision, so we can see that the M type data has been the best decided. So what to do with it? So this slide summarizes clearly that is our hybrid strategy. So by this strategy, we can give the best decision for the data with its corresponding locality, and we also perform the experiments. Later we can see that our strategy can give a very significant improvement for the cache hit rate and also improve the performance significantly compared to the previous scheme. So our experimental result is summarized in these slides. We perform our simulation using the full system simulator as introduced before, and the baseline we compare to is in same implementation without the cache management. And we can see from the result that in average, we can reduce the FPGA cache miss rate by 33%, which is quite significant, and correspondingly, we can improve the performance by 24% compared to the previous design in the reference paper. So our scheme can achieve like much larger improvement. Then considering the overhead about the controller, we can see actually because our controller is quite simple, so the resource usage is very small, and also for the control decision overhead at runtime because it is performed only at cache miss. So cache miss is quite long delay. So then our decision delay compared to the cache miss delay is quite small. So the delay overhead at runtime is also negligible. So then from the experimental results and the overhead analysis, we can see that our scheme is quite practical. And this is design is targeting the system like in Hub1 system, and we also have our design for the Hub2 system, the later generation, but due to the time limit, I will not introduce it here. So if you have interest, please refer to our group paper. To summarize, in this talk, we have introduced some of our works for high-level synthesis and the hybrid computing. And for high-level synthesis, we propose the automatic design space exploration framework, which can achieve the best settings of the design parameters. And for the hybrid computing, we mainly investigated on the different memory hierarchies for the CPU and the FPGA architecture, and we also trying to optimize further for the cache management of the FPGA cache for the shared cache CPU and the FPGA heterogeneous system. So for the time limit, we cannot discuss more, but I'm very happy to discuss with you further if you have any questions regarding my talk, and thanks again for attending my talk.